And so today is mostly going to be a review of stuff you've seen before, but it may have been a while since you've seen this stuff. So that's why I'm reviewing it. This is stuff at the end of chapter 2 and the first section of chapter 3. So we're going to be talking about periodic trends. And your book starts with ionization energy, and I like to start with atomic radius. So we're going to do that.
In the class, we're going to discuss like where the cutoff is for the quiz.
Yeah. Come on, open up. Where is power? Why are you not working? All right. Open sesame. There we go. Now it's going to open 4 times. Okay, so atomic radius is something that is a little bit counterintuitive. You may remember that we start on the left side of the periodic table and move to the right side of the periodic table, the numbers get bigger. So lithium, for example, is element 3, neon is element 10. So lithium has 3 protons, has 3 neutrons actually, 3 electrons. Neon has 10 of each, but neon is actually much smaller than lithium. You will see if this PowerPoint ever pops up here. So it's a little bit counterintuitive that what we think of as smaller because it has fewer protons is actually going to be the biggest one. So the biggest element in each group by far is the neutral alkaline metal. If we look at numbers for them, and I don't have numbers on the first slide here, but if we looked at numbers for them, lithium is actually larger than iodine. So iodine is the element 53. It's actually larger than xenon as well. So there's quite a bit of change. Now, the important thing to remember is this is for neutral elements. So we only talk about the neutral elements this way because it relates to the other periodic properties. The story of sizes changes when we change the charge on things. I don't know why that's being so slow. Okay. So the trend is from left to right, the radius decreases across the period. The trend going down is as we would expect it. Top to bottom, the radius increases. Now there is a little exception I'll get to in just a second. But before we get to that, why do the elements get smaller across the periodic table? I'm going to remember why.
Because of the shielding, it pulls it into the nucleus.
So shielding is important with size, but it's actually, before we get to shielding, it's because the nucleus has a more positive charge. So if we compare lithium and beryllium, beryllium has 1 extra proton. So we're going from 3 protons to 4 protons. So the electrons are pulled in more. And then this continues across the row. Oxygen has more protons than boron, and neon has more protons than fluorine. And so as we go across, it's pulling in more and more and more. But then we might ask ourselves, why then doesn't it just keep getting smaller and smaller? Why isn't sodium smaller than neon? And that's where shielding becomes a factor. So we do have a little bit of shielding as we go across. And that's why we might have things not shrink quite as quickly as we might think they would do. But remember, there's more shielding when we change layers. So as we change layers, it's going to expand because I've got a lot more shielding going. But something I want to focus on is the transition metals. So if we look at, let's take a look at the column with vanadium. Has a radius of 136, and underneath vanadium is tantalum, and that's 146. I think I got this is 30.
Niobium is in there.
Oh, tantalum was the bottom, sorry. Niobium is 146. Tantalum is also 146. So it is exactly the same size as the element up above it. Now let's look at the next column over, see if we see any differences. So chromium is 126. And then we have molybdenum and tungsten, which are 139 and 139. So the trend going right to left is the same, that it's decreasing in size, but going down when we get to that third row, we don't really see a change. And this trend follows pretty much across. They're pretty similar in size. There's one, zirconium, is underneath titanium. So titanium is 147. Zirconium is 160 and hafnium is 159. So we actually have not just a similar size, but it's smaller for the heavier element. Okay.
Is the NaCl in, I don't,
Yes, that's not so good.
and those are both 146.
This is niobium, this is tantalum,
And those are both 146.
and those are both
Okay.
146. Okay, so this is what's called the lanthanoid contraction. Sometimes you'll hear it lanthanide contraction. The ending "ide" is usually used for anions. So inorganic chemists prefer to use lanthanoid, but lanthanide has been around for so long that lots of people still use the term just out of habit. So the lanthanide contraction, I'll give you a definition since you can't see it on the screen, is the observation that the size of the third row transition metals is similar to the size of the second row transition metals, rather than getting larger. Okay, so there are a couple of reasons for this. So this is something we don't typically go into in freshman chemistry. This has to do with partially the periodic trends. So if we remember that there are the two rows, the lanthanoids and the actinoids that we put at the bottom of the periodic table, but they actually fit in between the transition metals and the S block, right? And where they go is right where lanthanum is, okay? So if we're thinking about that trend of things getting smaller going across, and we have 14 elements worth of things getting smaller going across, then it makes sense that by the time we get to zirconium and niobium and molybdenum, we would end up with something that was considerably smaller than we would expect. In this case, so much so that it reflects the same size as the other elements above it. Okay, so part of it is just we're decreasing in size. Part of it is also those relativistic effects. So remember that on Friday we had talked about the two no, it wasn't Friday, but it was a few class days ago. Talked about those two s electrons that kind of got stuck on the heavier p block elements, that they didn't come off very easily, and that was because they were moving so fast. They were heavy, right? They were approaching the speed of light, and so they were heavier. Well, that heaviness causes them also to be sucked in closer to the nucleus, and usually the s orbitals are the ones that define the size of an atom. They're the most extended. So with those being sucked in, then the overall atom is smaller. Okay, so our trend of the radius decreasing and relativistic effects are the two ways that are two reasons that occurs. All right. Next trend is ionization energy. Where are you going? Oh, I should just give up on this. Okay. So ionization energy, remember, this is the energy that is required to remove an electron from a neutral atom, technically in its gas phase. Okay. When we say that it's required, that means we have to put energy in the system in order to remove the electron. So if you think about the electron is negative, the nucleus is positive, we're pulling that away. So the things that are easiest to remove the electron from are going to be our alkali metals. And if you go back and look at this video, there's a graph here, and we have all of the alkali metals are in the bottom places on the graph, and that is because they have very low ionization energy. Well, they're also the largest atoms, so that means that those outside electrons are farthest away from the nucleus. Okay, so large means the electrons are easy to remove. Small, on the other hand, means it's harder to pull them away. And so our noble gases are the smallest ones in each row, and that's where it's hardest to pull the electron away. And so the trend is, in general, we increase in ionization energy going from left to right. Now, there are exceptions along the way. I'm not going to go into detail on those, but we did talk a little bit about how going from nitrogen to oxygen, we had that situation where nitrogen has the 3p electrons. So we had one unpaired electron in each of those orbitals and lots of possibilities for exchange. So we had that stabilizing exchange energy. But in the case of oxygen, we did not have that. And we also had the Coulombic pairing energy, which destabilizes it. Okay, so that's this mouse is not for my computer. So that's our general trend for ionization energy going across. It increases, and then as we go down, of course, the atoms tend to get bigger, and so it decreases going down. Okay, so an important thing to remember is that runs an opposite of the radius. The smaller the atom in general, the higher the ionization energy, and then the reverse. Now, every time we ionize something, we can ionize more than once. Obviously, we can have more than just a +1 charge. Every time we ionize, it's going to take even more energy than the last time. Because now, instead of taking an electron away from a neutral atom, we're taking an electron away from a positively charged atom, and that's going to require more energy. So the second ionization energy is always higher than the first, and the third is always higher than the second, and so on and so forth. That's kind of logical. But there are places where we see big jumps, and this usually happens when we're changing which orbital we're taking the electron out of. So if we think about sodium, we know sodium has one s electron. That first electron is coming out of an s orbital, but the second one is coming out of not a 3s orbital, but a 2p orbital. So it's a different orbital, and that usually causes a bump in the ionization energy. And the fact that not only is it a different orbital, it's a different energy level. So I'm digging into the core, that makes it even higher still. So when I have to take the core electron, it's going to be a huge difference in ionization energy, like 10 times as much instead of twice as much for the next electron. We talked about atomic radius. Remember that ions change size, okay? So what happens when I lose an electron? Does it get bigger or smaller?
Losing electron, I think it gets smaller because you have more pull on the other electrons.
All right, so Will says that it should get smaller because we have more pull on the electrons, and that is exactly right. We would have more pull on those electrons because we didn't change the number of protons, we decreased the number of electrons. So I'm gonna erase these numbers for the lanthanide fraction and put some other. Okay, so we said lithium was pretty big for such a small atom. It has a radius of 152 picometers. But if we have lithium plus, so we take away just one electron, then it goes down to 76 picometers. All right, so picometer compared to an angstrom, remember angstrom is 10 to the minus 10. A picometer is 10 to the minus 12. So we've just moved the decimal by 2. So atoms tend to fall in the range of 1 to 3 angstroms. And so the lithium plus is a little bit smaller than 1 angstrom in radius. Okay, so it changed by about half, going from neutral to positive. The change isn't quite so dramatic as you go down, but it is pretty big. Let's see, sodium goes from 186 to 102, or it's a little larger than half. And then if we look at cesium, we've got 265 to 167. So cesium's the last non-radioactive. Yes.
As your ionization energy goes up, so like say you're going from like a fluorine minus, and you take an electron off of that, will your radius decrease by even more?
That's a really good question. I don't have data on that, so I'm not entirely positive. I will look into that. But yeah, that's a really interesting question. All right, so Will was asking if I compared things that had different ionization energies, will I see bigger differences in the radii? So I will have to look into that. All right, so positive charges, cations, tend to be smaller. Now, if I compared this to the 2+ ions, I've got even bigger difference between protons and electrons. And so the 2+ are generally going to be smaller. So my magnesium is 72 compared to the sodium, which was 102. And so the magnesium 2+ is actually a little bit smaller than the lithium plus.
What's the magnesium neutral?
Neutral for magnesium is 160. So that's actually less than half of the original magnesium. And then if I look at barium, I'm going from 222 for neutral and 135 for the 2+. So as a general rule, within the same row or period on the periodic table, the 2+ will be smaller than the 1+, the 3+ will be smaller than the 2+. Now, I can't say that all 2+ are smaller than all 1+. If I look at barium, it's 135, and sodium plus is 102. And that's because it's so much further down on the periodic table. So really, that's just a comparison in the same row. Now, if I look at the anions, I'm going to see the opposite thing happening. So now I've got the same number of protons trying to hold on to more electrons. And so it's harder for the proton to keep track of those things. All right, so let's take a look at oxygen neutral is 73. So that's pretty close in size to a lithium ion.
It's the same number of protons, but more like.
Correct. When I add 2 more electrons, it just about doubles in size. It becomes 1/4. Lithium, little bit smaller than oxygen, starts out at 72. I'm sorry, not lithium. I looked at it and said fluorine, yeah. Fluorine starts out as 72. And it jumps to 133. So why didn't lithium, I'm sorry, I keep saying lithium, why didn't fluorine become larger than oxygen?
It only gains 1 electron.
Exactly. So it's increasing by 1 electron instead of 2 electrons. So it gets bigger, but the more electrons I add, the even bigger it gets. So the nitride, which is a N-3, is a 146. So notice though that I'm going from 133 to 140 to 146. There's not a big dramatic change in the size for my negative ones. It does get larger, but it doesn't get a whole lot larger as I add the electrons. Whereas when I went from +1 to +2 to +3, it was a pretty dramatic change. All right, I had really wanted to look at some data with some numbers here, but since we can't all look at it, I might save this for Wednesday. The gist of, these are tables at the end of chapter 2 that are just comparing the ion sizes for different groups. So it looks at the alkaline metals, it looks at the alkaline earth metals, so on and so forth. But it just reinforces the idea that the higher the charge, the smaller the ion is going to be. Let's see, what's the next one? The next slide that I have looks at titanium 2+, titanium 3+, and titanium 4+. And so the radius goes from 100 to 81 to 75. Let me write that down. 2+ is 100. Titanium 3+ is 81. And titanium 4+ is 75. Okay, so same element, but as we continue to lose those electrons, it gets smaller and smaller, reinforcing that idea. All right. Next thing is electronegativity. I know this is something you talk about in other classes. What's our most electronegative bonding element? Fluorine. And so on Pauling's scale, and most scales kind of reflect Pauling's scale, that's a 4. So this isn't a measurement of energy or anything. This is just, we made this scale and arbitrarily set 4 as our highest number, and fluorine has that. We can assign electronegativities to the noble gases. And as you would expect, the trend continues. So neon is higher than fluorine and helium is higher than that. But because electronegativity is described as the ability of the atom to attract the electrons in a bond, and because noble gases don't tend to bond, we normally leave them out of that picture. But we've definitely been able to make xenon compounds that have some bonding going on, krypton compounds, and I think even argon compounds. So our heavier noble gases have been able to bond, and so we can look at that electronegativity. Yeah.
Does that have anything to do with like neon signs? You know, if you're, because I know you put
Only
like,
very loosely. So in a neon sign, basically you have a glass tube that is filled with neon. And then there are other signs that we sometimes call neon signs that aren't really neon, they're just a different gas.
more fluorescence than like ionization.
And so, well, there is some ionization going on. So they send electricity through the gas and it rips off the electrons, but it doesn't rip off the outside ones. It rips off the core electrons, the ones on the inside. And so as those electrons are pulled from the inside, the ones that are on the outside sort of trickle down into those spots. And that's what releases the light. And so for neon, that is a characteristic, very intense orange color. So it's only when you see orange that it's actually neon. And then different colors are because of different elements. Okay. So with electronegativity, one thing that we kind of gloss over as freshmen is that we don't have this really nice trend the way we might think of it. So fluorine is the highest, and it does tend to get smaller as we move away from fluorine. But there are transition metals from ruthenium over to gold, sort of that rectangle there. Ruthenium's in the second row, gold is in the third row, that are fairly high electronegativities. And so they're above 2. And in fact, gold's is 2.4. So how high is that? Well, carbon is 2.5. And carbon is a non-metal. So gold and carbon have very similar electronegativities. And hydrogen is 2.1. So that means that gold, a metal, is more electronegative than iron or than hydrogen. Okay. And so that affects the way that those elements interact with certain nonmetals. And that's probably one of the reasons why we can get platinum is often used as a catalyst for reactions involving hydrogen or hydrocarbons because we have similar electronegativities. All right, so later on in chapter 3, we're going to be talking about some differences in the way different elements bond. And so we'll be talking about whether we have long bonds or short bonds, or whether the bond angle is large or small. And one of the things we will keep coming back to is the electronegativity of the atoms. So we want to think of it both in terms of the size of those individual atoms. Smaller they are, they tend to be more electronegative, but also in terms of we're drawing electrons from that bond. So rather than that bond being like a stick that's the same size on both ends, it's really more like a baseball bat or a wiffle bat, where it's, you know, a little bit wider on one side and a little bit narrower on the other side. And so where those electrons are is going to make a difference for what happens with the bonds. So that's something to keep in mind. I think that was my last slide. Yes.